Okay, welcome to lesson 10 on oxidation and reduction reactions. And oxidation and reduction reactions are commonly referred to as redox reactions for reduction and oxidation, whatever. Anyways, in class we did a great activity using something called the Dradio. I'm going to show you a video of one of my favorites. Go. Yeah! Give him a hand! Alright, so the Dradio is great and we were completing an electrical circuit, but there was one thing that everybody was taking for granted. Think about it for a sec. What were you taking for granted? Yes, the freaking battery. The battery, folks. You guys were all taking the battery for granted. Actually, I don't know if you were or not, but let's just assume we were all taking the battery for granted. Now, what is inside a battery? Okay, how did those electrons just move and fly out of the battery? Well, we know how we get energy in general.
Carefully matching every child to their ideal monster to produce superior speed.
I mean, it's kind of ridiculous. That right there is not a battery, but it turns out it is very, 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 very similar to how we get the energy from a battery. Okay, so let's look at what's inside a battery first, and let's look at it qualitatively. Okay, so if we look at a typical AAA battery like the one in the Dradio, okay, the battery does a couple things that are really, really important. Okay, one, it produces spontaneous redox. Okay, what that means is there is a spontaneous flow of electrons coming from the battery. So let's define what I mean by spontaneous. By spontaneous, what I mean is free energy. Energy that just happens. It just flows. It just is given to us just because it exists. Okay? And by redox, what we mean is the transfer of electrons. Okay? Now, instead of kid screams and trapping them inside a bottle, what we're doing is trapping this spontaneous flow of electrons inside a battery. But it's very, 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 very similar to that canister of screams. Okay. Now, there is an equation that we use for free energy, and that equation is delta G. Delta G stands for Gibbs free energy. And for the transfer of electrons, we use something called E cell. Okay, so E cell is the voltage of a battery. So if a reaction produces free energy, we actually have delta G with a value that's less than 0. So that means that there is, it's just producing energy. It's not taking in any energy. So if delta G is less than 0, E, the voltage of a battery, is greater than 0. So if you go into a store and you say, okay, can I get a 9-volt battery? That's a positive voltage, which would result in a negative delta G. So if somebody asks if a reaction is spontaneous, we will say yes, the delta G is negative. That's because the voltage is positive. Similar to a AA battery, which has 1.5 volts, and a D cell, which I think is 6 volts, etc. Okay. So let's look at this in terms of an equation now. Right, so if we look at this battery right here, and we know that it's producing spontaneous energy, and it does that from a positive voltage, E cell, we can derive an equation for it. So the delta G is equal to the product of the moles of electrons transferred multiplied by this constant called Faraday's constant, with a negative in the front here. So if you notice, the negative in the front allows us to have a positive voltage yielding a negative delta G. And the units on this guy here are always going to be joules. And often it's converted to kilojoules by dividing by 1,000, and that's going to be the kilojoules. Sig figs apply. So let's go ahead and label what these things are again. Again here, this is the free energy. And if the free energy is less than 0, the reaction is spontaneous. If the free energy is greater than 0, the reaction is non-spontaneous. So we're looking for this for a battery. All batteries are like monster screams. They're going to produce free energy sitting there in that battery. We took it for granted. It was just giving us that energy. How awesome is that? This is the moles of electrons transferred. This is the voltage in V. And this is Faraday's constant, and the value is just 96,500. Now, rather than giving you a bunch of units, just know that this whole thing comes out in joules. Okay? So let's go ahead and do an example of how we would calculate a problem like this. Okay? So in order to do problems like this, you are going to be given a chart called the standard reduction potential chart. Okay, and we'll get to that in a second. So let's look at what might be happening inside this battery. Okay, and it turns out that inside every battery you have a spontaneous redox reaction, which means free transfer of electrons. And what we're going to be doing is we're going to be harnessing those electrons. So a really common reaction is the zinc-copper battery, where you have the reaction, the solid zinc metal. I'm going to put a 0 at the top to show you that actually this zinc here has no charge. It's got an equal number of protons and electrons. And that's reacting with copper sulfate solution. Okay. And that reaction is now going to be producing a single replacement reaction, zinc sulfate, and now copper solid. And I'm going to put a 0 at the top. Okay. Now let's look closely in that reaction diagram as to what is really happening. Okay. So in this case, we have two cells. And in this cell, solid zinc is reacting with aqueous copper sulfate. It's aqueous, so let's show it in its ion form. Copper 2 plus, SO4 2 minus. And on this side, the products we've produced now copper solid. I'll draw that over here. And why don't I go ahead and put the little 0, high 0. And now we have aqueous zinc sulfate. So Zn 2 plus, SO4 2 minus. Okay, so what's happening in here? Well, what happened in here is the Zn had an equal number of protons and electrons. And the Zn transferred electrons over to the Cu. And how many did it transfer? Well, it needed to reduce Cu down to 0. So it transferred 2 electrons. Okay? So this battery here, this battery harnessed the spontaneous transfer of 2 electrons. Okay? These 2 electrons being transferred spontaneously, having a delta G less than 0 and an E greater than 0, allow this battery to work spontaneously. So let's focus in a little bit more on exactly what was happening in those beakers. Now we have the reactants and we had the products. Okay, it's really the same beaker with the reaction happening, but who's counting here? And you can never get too good at drawing diagrams like that. Now, for the sake of this, I'm going to put the sulfate up here. Now, it doesn't mean it's not there. It's still present, but this sulfate is not participating in the spontaneous transfer of electrons. Okay, so we're not going to worry about it. So what we had was Zn, 0, solid, and that Zn, 0, solid, transferred its electrons to Cu2+. Okay, it took 2 electrons, boom, and it transferred them, just like that. Okay, and what we were left with is we were left with Cu solid now, and Zn 2+. Okay, so that's what we were left with after that process. So the trick is, how do we turn this into a battery diagram and calculate the voltage? We're going to learn half of it in this video right now. So let's break these two processes down into what is happening to Zn and what is happening to Cu. Okay. So what is happening to Zn is being oxidized. We're going to call that ox. And we're going to call this the oxidation half reaction. Okay. So for the oxidation half reaction, Zn is starting as Zn solid with a 0 charge, and it is going to Zn 2+, which is now aqueous. Now the sulfate's there, we're just ignoring it right now because it's not involved in the spontaneous transfer of electrons. Now what happened in order for it to be able to do that? It was oxidized. And there's a couple ways of looking at oxidation. First, it lost these 2 electrons. Okay, it lost them, and we show that by making the electrons products over here. Okay, it lost those 2 electrons. Another way of thinking about it is its charge went up. It either goes from negative to 0 or 0 to positive. Okay, so that's the oxidation process. Now what happened to Cu? Well, let's take a look at it. Cu, which is right there, started as Cu2+, aqueous. Now remember, there's really a sulfate flying around there, but we're not worrying about it because it's not involved in the spontaneous transfer of electrons in the battery. Okay. And it became Cu. Well, what happened to Cu? Cu took those same electrons, these electrons. So these electrons right here, ooh, were grabbed onto by Cu. Okay, a lot of times people think in these half reactions it's the same different electrons. What am I talking about? That it's different electrons. They're not. They're the exact same electrons. And this is the reduction half reaction right here. So what we can do is we can add these up and get a total net reaction. So in this case, that's going to be Zn0 plus Cu2+ goes to Zn2+ plus Cu0. And this is the net ionic or net redox reaction. Remember, the SO4 is still there. It's hanging out right here. And it's hanging out right here. We just don't care about it because it's not part of the redox reaction. So what a battery is really trying to do is a battery is trying to harness this right here. It's trying to get something right in between there. In your case, it was, the circuit that you created. Okay, it was what you saw Bruno playing right there, and Brittany taking the nice little vertical video of it. Okay, it's a flashlight. It's whatever you're charging. But the trick is to shove something right in between that spontaneous flow of electrons inside the battery. Okay, So let's learn how to calculate the delta G for this reaction, and then we're done. Okay. So we know that in this reaction, the oxidation half reaction was Zn goes to Zn2 plus 2 electrons. And we know that the reduction half reaction was those same 2 electrons grabbed onto Cu2 plus and go to Cu0. Okay? And it's reduction because you're gaining electrons, and it's oxidation because you're losing electrons. Oil rig. Oxidation is losing electrons. Reduction is gaining electrons. Okay. So all we have to do, each of these is going to have a voltage value. Each of these values. So you're going to have a voltage value here and a voltage value here. And all we do is add them up. Okay. You don't need to worry about the number of electrons or anything. Okay. The trick is, on the chart that I showed you earlier, everything is written with respect to reduction. It's called the standard reduction potential chart. So what we have to do is always put a negative in front of the value for the oxidation half reaction. And then we simply add them up, and we get the total value, which is the E cell. Okay. So let's look at this reaction right here. So what we got is, here's the half reaction for Zn, and here's its value. Okay, and now there's a couple Cus. We're looking for the one that has Cu2 plus going to Cu0. Okay, so that's not that one. That's going to be this one. Okay, so remember, the zinc, okay, was the one that was oxidized. So we take the oxidation half reaction and we make it negative, and we take the reduction half reaction and we just add it to it. So this one was right here, negative 0.76, and the copper was 0.34. So the overall voltage is 1.10 volts, and that is your E cell for the reaction. So let's go ahead and calculate delta G. So in this case, delta G is going to be equal to negative N F E. Now you're going to see at times a 0 up here, and that just means the reaction is happening at standard conditions, 25 degrees Celsius. So let's go ahead and do it. We know that the half reaction is Zn plus Cu2 plus goes to Zn2 plus Cu0, and we know that that happened because of the spontaneous transfer of 2 electrons in the battery. So that means that N is 2. We know that Faraday's constant is 96,500, and we know that E cell in this case is 1.5 because we took the oxidation half reaction and we made it negative, and we added it to the reduction half reaction, which we kept the same. And that's going to be 1.10 volts. Okay. And this answer now is going to be something joules. And now notice here, because this is positive, okay, because the E cell is positive, delta G, in this case, is going to end up being negative, and the reaction is going to be spontaneous. So, So let's go ahead and do a little summary right now. Number one, batteries produce spontaneous redox, okay? Which means a battery produces free energy because the electrons are transferred freely, and the whole point is to be able to trap that. There's an equation that's used to calculate this, where this value right here is the voltage, and this is the free energy. this is always going to be negative for a battery, and this is always going to be positive for a battery. Okay? And we're going to learn how to draw those battery diagrams in class, but the trick is to put something between the spontaneous redox. So the Dradio, you were putting yourself in between the spontaneous redox. We can put a lot of things in there. Okay. So for the multiple choice question, we're going to do something a little bit different for this one. We're not going to do a multiple choice question. I want you guys to write a summary of this video in the box below. So for the first part, tell me what this video was about. Give me a one sentence, just this video was about. Tell me some things that you really understood, and then give me a sentence about the things you really struggled with. And then questions that might still remain for you. Now, if you really get it, I want you just to expand on that. Tell me why you really get it. Thanks.